So thank you for inviting me. My name's Danny Williamson, and I'm the PI of a project called UQ for COVID that came after RAMP. So sort of involved with RAMP, and we got connected with Leon Dannon, who is one of the guys at Juniper and a modeler with SPI-M. And we got all of the technology ready to run big COVID simulations, and we put in a grant to say, we're going to make real-time uncertainty quantification available for a particular model in SPI-M so that it could be used to answer questions. The ones we suggested in the proposal would be optimal vaccine rollout strategies or testing local lockdown interventions, because this was summer 2020 when we wrote it. By the time it was funded, the over 80s were being vaccinated, and local lockdowns had sort of been tried and have been binned for policy reasons. But there are plenty of other things to work on. So let me give an introduction to the idea. So everybody knows that models were used to inform pandemic policy. We all watched briefings, we saw projections from models, and we kind of, in terms of the public consciousness, we were aware that SAGE were providing this information. And if you listen to Chris Whitty or Patrick Balance, they would mention quite frequently SPI-M, which was a part of SAGE where all the modelers were. And how you get onto SPI-M, and I'm not on SPI-M, so at some point what I'm saying may drift in terms of accuracy. But you need to be an infection modeler with an appropriate track record and a model, and then you volunteer. And it's important to note that very good people are volunteering like all of their time and weekends to do this in very short order. So anything I say sounds critical of what happened or what is happening, not meant to be, but my topic is uncertainty quantification. I left my first degree. Uncertainty quantification is the topic of how one combines data with models, say something about reality. Subject. Many of you in the room will know some or all of the main ideas. And it wasn't used at all for the models in SPI-M, and still isn't, as far as I know. I could be wrong, but I don't think it was distressing to many in the community at the time when these were being used, and a lot was made here at the Newton Institute with RAMP to try and get us involved to help. My project is some effort to do that and to actually help in real time, not just for the next pandemic. The reality is the turnaround time for contributions is so short that, well, as we'll see, maybe I have done a lot of rethinking about what UQ needs to be like in order to have this kind of impact. This isn't going to be a talk that says, here's what you should do, and we figured out, and here's an example of us doing it at the end, it's done, and why don't you use this? It's much more going to be, I thought we knew how to do this, here's what we've tried so far, and why it doesn't work. So someone else coming after me might actually give a talk saying, oh, we did it all, and it works, it's great. So if that's you, congratulations. So MetaWards is the model that we're using. Any model that's on SPI-M, they're all different. This is one, and it's a framework. So you don't just have an infectious disease model, you have a framework, a way that you model, and you put your model together on the basis of the disease and what you're observing and the questions you want to answer. So the broad brush framework is SEIR in every electoral ward in England and Wales. There's over 8,000 of those. People move between wards according to where they work and how they play various matrices and so on. And when any new infectious disease comes along, a custom model can be created. So here's the one that we're using. You've got this I class here, that's a bit more complicated than normal. There's an asymptomatics class. Those that are infected and are sick could either sort of start to recover but remain infected for a while. You might die, or you might end up in hospital, and so on. Now, early in the pandemic, it was very easy in Metals just to add a class. We had one for ICU beds, because the main question at the time was, are we going to run out of ICU beds? Have an ICU class. In the first go, this wasn't an age-structured model. This one is. There's 8 age structures, because we're trying to work out kind of vaccine strategy. So you need different people of different ages in the model, and so on. Now, I would never be setting this model up. This is what the infectious disease modelers do. They have a framework, they have code, they put together what they need to answer the question, and then all of the things inside, the parameters and so forth, would need to be calibrated data. And you would have to do it quickly, because with SPI-M and so forth, this week's question is not interesting next week. There's another question next week and another one the week after. Pandemic moves fast. This is what a simulation looks like. It's only to give you a notion of the spatial scale. I'm not showing a video. It's not particularly important. It's a big model. We run it on a supercomputer in Bristol. All the data that comes off it gets stored on Jasmine. There's a lot it takes to set that kind of structure up, but RAMP helped a lot less in the summer of 2020. So I come at these problems from a UQ point of view. Some quick notation. Be interested in a physical process. I will always call that Y. So Y will be kind of the truth of COVID, if you like. You would have some observations of that process. For example, you know how many people died in hospital, how many died in the community, up to some error. And then you have some sort of model that I'll denote F now, with some parameters that is supposed to inform you about the truth. So that's the sort of start of a UQ type framework. And the big questions are, well, how informative is the model for truth? And what should the parameters of the model be? Now, UQ has made at least two, but the two big contributions in this area are, one, model discrepancy and how one calibrates models under model discrepancy. That'll be the next slide. And the second is emulation. So how do you deal with expensive models? So the key idea here is that you say that the truth is equal to the model at some best choice of the parameters plus a discrepancy term. So you acknowledge immediately that the truth is not the same as the model under any circumstances. And with COVID, you'd have to do that distribution. You're able to, via some method or other, calibrate the model. There are two competing, popular in the UK today. One is to sort of either give a normal or Gaussian process approximation on the calibration that updates parameters. The other, called history matching, is again to quantify the discrepancy and then cut away all the parameters that couldn't possibly lead models that look enough like reality that you would care about them. The two approaches, it doesn't really matter which one you're in favor of for purposes of this talk. The key point is, without discrepancy, any inference about the parameters is just wrong. And well, much has been made of that over the years. It's our core contribution, I would say. Now, if you want to do any of these algorithms, if you want to estimate the posterior distribution of parameters, or if you want to be able to cut out lots of parameter space with a model that takes like a whole night to run on a supercomputer, so what you do instead is you build an emulator for it. And cue the second contribution. 35 years of this idea of taking a model and representing it some sort of Gaussian process where the kernel structure is up for grabs, the mean is up for grabs, the dimension of this F is up for grabs. But what it's doing at its core is you take a true function, the black line, you observe it partially, and with a Gaussian process prior, you can update your beliefs about this function using those points to get a blue line, which would be your mean for the function, and some uncertainty. Now, obviously, my 3 points here, I've got loads of uncertainty. And that pri can be constantly updated with more data until your distribution over the functions lies nicely over the true function. And now you have a statistical model that's super quick to draw from, rather than needing a supercomputer to run. And you can do your analysis with the emulator, propagating any uncertainty that you still have through your analysis. And obviously, I've drawn this in a simple 1D on the output case, but we've done this, and many other groups have done this for very complicated things. So there's a sort of 80,000 grid cell representation of the UK land surface that we just had an emulator published for now. So a prediction gives you 80,000 cells over parameters. You can sea level pressure, where you, to build the emulator, you project all the model output onto a basis, and then you just have to build a few emulators of coefficients. There's a lot you can do with this technology. However, to do it for COVID. So we're tooled up. The project started. We've got infinite compute time on the Bristol supercomputer to run the model. We've got infinite storage, thanks to NERC on Jasmine. We've got a team of UQ specialists with all the code that knows how to do this. And all we have to do is calibrate the model so that we can start helping the people on SPI-M who run MetaWards to answer important questions. And we gave ourselves in the proposal 6 weeks. That was over a year ago. And we started to see things like this, which makes us happy. So we have log deaths here, log hospitalizations. And this kind of window is where we see the observations up to that sort of model discrepancy and model error. So we're seeing model runs. Remember, this is 8,000 odd wards. When you average over the country, or you sum them, in fact, you see some model runs that are okay. These are for low values of R0. Of course, all the other parameters are changing at the same time. And you see loads of model runs that are not okay, which is really good in a calibration sense because it gives you a nice focused prediction of where in the parameter space you are. All looks like everything works as normal. And you start to look by region. So now I've colored all of the points that were in that Goldilocks square of good stuff. I've plotted those in green, and the black dots are where the actual truth is. I should say, by the way, we're running up to lockdown number 1. The idea is we demonstrate that you could calibrate a model up to lockdown 1, and the calibrated predictions would be formative for what you should do at lockdown. Because if you can't do that, then UQ couldn't have been involved at the start of the pandemic. So we thought we'd just do this as a demonstration. The true number of deaths. The green points are close enough that with a few more iterations of searching, we pull them down. And then we saw this plot. This is the proportion of deaths of the total in each region. And it doesn't matter what you do, you cannot make the model get enough deaths in London relative to everywhere else. What happens is, London, the pandemic takes off, and it never does in the model, and it doesn't matter what you do to the parameters at all. So now you have two choices as when you see that. Either you can beef up the model discrepancy and allow the model to say anything, and therefore get no good calibration, but at least you quantified the uncertainty. Or you panic. Let's look at what the data is looking like. So we have deaths here, we have cumulative deaths here. These are the real deaths, not the model. And as we go through March, you see this nice theoretical exponential growth that you would expect. What happened was, in the east and the southeast, there were 1 or 2 deaths early on. But the deaths never really took off. They went slowly. And then all of a sudden, London takes off. Now, why can the model not do this? Model can't do it because the model has lots of missing processes. The model, you start it by seeding it somewhere or in a few locations. And we've spent months trying to get the seeds right to get it to do this, and it doesn't. You start it off seeding in a few locations, you run it forward, and you try to get it to take off. But in reality, that's not happening. In reality, people are constantly bringing COVID into the country from wherever, and probably more into London than elsewhere. And maybe there are other processes that aren't in the model that are bringing into COVID. And there is an outbreak. We expect outbreaks in reality that are not in the model. And maybe there are outbreaks in the model that are not in reality too. So we could say, well, why don't we just run the model longer, way past lockdown, get all of this outbreak stuff out of the way. And then when there's enough cases and deaths, then we'll be able to calibrate it really well because all of that noise of individual outbreaks will be gone. And yeah, we did that in summer in 2020. You can do that, but it didn't answer the question of what we should do now.
Danny, you've got 5 minutes.
5 minutes, I will wrap up. Or I'll wrap up in 5 minutes. Okay, so what do they do when you have this problem? So the problem is that small errors in your state vector in COVID and indeed in weather forecasting quickly blow up out of control. Even if the parameters are correct. Now, NWP has the same problem, and it took 40 years, but they have really good solutions based on data assimilation. So data assimilation is the idea of constantly trying to nudge the state vector towards the observations, because you acknowledge that there are processes missing in the model, and because there's a sensitivity to the initial conditions which are uncertain. And it works like this. It's done in ID modeling as well. They're known as, they're more commonly known as particle filters in statistics and infectious disease modeling. So what you do is you run your model for a bunch of climate, people will call them ensemble members, or we'll call them particles. And then you combine them with observations using your favorite particle filtering method, and you get a sort of result. And then you restart the model, or you start it at the next integration from this nudged state. So you don't ever let the model just keep going. You intervene and you move the states towards the data, not actually onto the data, towards it, and so on. So how this would work, if you assumed your model was perfect, you have an observation error distribution like this. You have a perfect model like this. So this would be my meta-wards. That assumes that if I knew the parameters, then the one-step transition is coming from the model. And this is a kind of particle filter that would lead you to estimate the posterior distribution on theta star. So you can't evaluate this likelihood, but you can simulate from it. And the way you would simulate from it is this data assimilation idea. So you start from an initial state, you run the model forward, and then you do that for a whole bunch of particles and reweight them according to this, this data error distribution. So that's the perfect model, and I think that's what some infectious disease models do to calibrate, but it ignores discrepancy. So you could calibrate like this, but you wouldn't have discrepancy in there. And the big innovation, I think, in numerical weather prediction is building in that model error. I'm going to have to skip our model error distribution for this because I only have a few minutes, but we came up with one based on a discrete version of a measurement error model. So there are parameters in 2 Poissons and gives you count distributions on error that are reasonable. So you have, I'm probably going to end the talk almost here and skip to the lessons. For a joint likelihood where you have discrepancy, the procedure is as follows, and this would change the way infectious disease and change the way we do UQ. So you have your infectious disease model here, your COVID simulator, and at every time it takes the current thing that you think is happening, so reality, and iterates it one step. You then simulate from your discrepancy process, whatever you think that ought to be, so you add some error that accounts for the fact that things are going wrong and gives it some wiggle room. And then you update the particles however you normally do that. And of course, so once you view it as a data assimilation problem, this is how you do it if you knew theta star. The parameter estimation problem has essentially 3 options. Option 1, add theta to the state vector and update dynamically, which they've been trying in climate prediction for a while, and some would say it doesn't work. The UQ way, which I was at first attracted to, is to sort of split your data, do some assimilation, and then try to do the usual calibrate stuff observed. And the thing that we've been trying at the moment, just emulate that likelihood and calibrate to it. I don't know what the right answer is. But I do know that if you look at our simulations, here we have the blue lines here are deaths that we're showing to the model. Everything else is a hidden state, and the red is the truth. And when you go with model discrepancy or without, the without discrepancies to capture what's going on in breaks in reality that are not. So there's something in this. The rest of the slides are an attempt to target the space where it's going on. I'm going to have to skip to the end. So these slides are these models are still models. UQ is still important. They're not that special. They are still models. But this nonlinear sensitivity to initial infections is just like the problems you have in weather forecasting with seeding in initial state. So some form of data assimilation, I think, is essential. I can't get it to work without any. And if we're going to do this for the next pandemic, we need to build these systems now together with the infectious disease. You can't build a data assimilation system on your own as someone who knows data assimilation. And you can't build it on your own as someone who knows about infectious disease modeling. We need to do it together in order to be ready. And if we don't try to buddy up with our favorite infectious disease modelers and get it going now, when the next pandemic comes around, it will be the same story as this time. A bunch of hardworking people doing it without UQ on their own. So let's try and buddy up and
the protocol here is to ask people in the live audience first for their questions and then seek ones from our colleagues who are remote. So I'm looking, and because we're probably going to be around for 3 days, it's great if you tell us who you are before you ask your question.
David Sexton from the method. So you mentioned the discrepancies there because you're missing some processes. So you're putting a model discrepancy now, or you're trying to calibrate or get some sort of discrepancy term in there. Do you learn in any way from that discrepancy term, kind of maybe where you need new processes?
It's a good question. I think with infectious disease models, that the process is simple. Like the big sources of discrepancy in our model are, I'm going to skip back to that picture of the model app because it's quite useful. So it's England and Wales only. So there's two really big cities here that aren't in the model that are probably exchanging infections with at least the northern wards and so on. So we're missing two big cities. That's one huge source of discrepancy. Another is seeds are sort of fixed and then the model goes and is self-contained, whereas actually in reality things are being imported. There's another sense of waning immunity that's not in there yet, but of course you could put that in. You wouldn't want to put in the whole world. It's a similar story as in climate. So I think learning the discrepancy and then learning to live with it and quantify it rather than trying to make the model more complicated is the way forward. Because otherwise you're going to have to put schools in there, you're going to have to put communities and hospitals, and just everything would have to go in, because you'll never get like everything in a model. And if you did, I'd still say there was a discrepancy, by the way.
Hi, I'm James Hetherington. I'm the Director of UCL Advanced Research Computing Centre. At the time this was going on, I was seconded from the Turing Institute to the Joint Biosecurity Centre. So I was seeing some of this from the inside. What were your experiences of the way in which the target model that you were trying to build a UQ scaffold around was realized computationally in terms of it being, did that cause issues for the ability to try and add some of these other techniques to it? Some of the really good epi models that we were working with, you know, were great scientifically, but it was quite hard to get modern tooling around them to bear on them, some of that.
Yeah, I mean, in truth, most of our year and a half working with the models was to run them as black boxes and use supercomputer frameworks and so forth, and then try to do UQ around them. And we've only really, the last few months, coming around to the idea that it's just never going to work. So that's what I'm
interested. If you can't black box them, it's.
I don't think you can black box them. So I think how we unpack the box and build the UQ scaffolding inside is both critical and far from obvious to me. And it's certainly not just stats and epidemiology in there. There are other disciplines.
One of my favorite models that we were working with was a homemade probabilistic programming language that had been accidentally created by an epidemiologist during their PhD in R.
Yeah, they do good things though.
Yes.
Right, so Claire, I think you're signaling there are people wanting to ask remotely.
I've got one person to ask a question. It's Michael Dunn. I'm just requesting to unmute you.
Yeah, sure. So my name is Michael Dunn. I'm a PhD student at the University of Exeter, and Danny's my second supervisor, actually. So I noticed that, well, obviously Meta Wards deals with, you know, these thousands upon thousands of wards, and it obviously gives a lot of output data. Do you think that there's almost, you know, obviously we've got almost like national models which model the country as a whole, and we've got like this kind of model on the other end of the spectrum? Do you think maybe the future of doing UQ on epidemiological models maybe lies somewhere in between? So instead of you know, 8,000 wards, it's, I don't know, the 650 parliamentary constituencies, or, you know, another way of breaking the country up?
Thanks for the question. I think as a statistician, I'm going to have to hide behind the modelers. If they think it's necessary to have at least some models like people, then I think it's necessary for us to put uncertainty in them. And if we can't do that, we should be asking ourselves why, not saying, can we make it just a single curve? Yes, we can emulate a single curve. That's easy. If the modelers are saying we also need things at these resolutions, maybe to inform decision makers for some reason, then we need to tool up as well so that we can deal with them. I think that's my answer.
Okay, thank you.
Thank you. Claire, is there anything else remote sources?
I've got two, but I think you might only have time for one more.
Let's take one then.
So I've got Ian Vernon. Would you like to ask a question?
Hi, can you hear me okay?
Yes.
Fantastic. I'm Ian Vernon. I'm at Durham University, a fellow UQ person. Thank you very much, Danny, for a very interesting talk and your sort of honest appraisal of the situation. I guess I'm going to sort of echo David's question a little, but do you not worry when you employ sort of data assimilation and you know the fundamental dynamics of your model are really not capturing like a major event? Do you not worry that this, well, data assimilation always fixes things to a certain extent, but really your model is always pulling you in a different place? And do you not worry that as soon as you unleash the shackles of data assimilation, then your predictions will resort back to those broken dynamics and bang, you'll be in a bad place? So I guess my question is, how do you judge when the model is flawed enough that using data assimilation is essentially dangerous and really fixing the model is the way forward?
It's a good question. In terms of the very last thing you said, how do you judge? I don't know the answer, and I think the expert needs to sort of at some point say, oh, we can't use this, or we can. In terms of ID models and the one that we've been working with specifically, it has the processes of people being infected and infections growing and propagating through the system down just fine. What it doesn't know is how outbreaks started. It can't seed its own outbreaks, and maybe whatever seeded the outbreak was actually many more people coming in, for example, or a particular factory in Leicester, or something that could just never be in the model. And it's those things where data assimilation can tell the model, no, we need to start from here, or you've missed this thing that happened that could never be in the model. We'll put it in and then tell us what the, use your fairly good, well understood scientific principles to say where we go from there. So I'm not particularly worried in these types of models about this question, but I think it's still a very important question. Whose answer, I don't know.
I think we need to stop there. Intriguing questions. And let's move on to the next speaker. Thank you very much indeed. Are you ready? We need to configure your presentation, or is it jumping up in front of you?
Just